before start, as usual, I ask you if you have any questions. Otherwise, today I would like to propose a couple of exercises in the form, well, actually, what I'm going to do is take one of the written exams of last year and, well, with a few modifications due to differences in program, I would like to propose it as an example of what you might see this year. Other examples will be posted on the website in the next days. Oh, by the way, I have to skip the lesson of tomorrow. So tomorrow's lesson is cancelled. I'll try to remember to also send an email, of course. Let me propose this example. Here in this exercise, we have 5 friends. Okay, in the exercise they are called Al, Bob, Chuck, Dave, and Ed. Okay, and they like to play some trading cards game where each of them has a deck of cards, basically. The idea is that in order to make the game more interesting, they decided to exchange their decks of cards every day before playing, according to these rules. So, the idea is that each of them has a deck of cards. So, these are the cards seen from the side. And they redistribute the cards in this way. Al splits his deck into 2 parts and gives the 2 halves to Bob and to Dave. Okay, let me write it here. A gives 1/2 of his deck to Bob and 1/2 to Dave. Bob splits his deck in 2 parts, equal parts, and gives his parts to Chuck. So 1/2 of Bob's deck goes to Chuck, and the other half goes again to Dave. Chuck gives his deck to Bob. So the whole deck of Chuck goes to Bob, and Ed splits his deck in 2 equal parts that go, okay, 1/2 goes to Bob, and 1/2 goes to Al. Okay, I forgot, Dave gives the whole of his deck to Ed. So the whole deck of Dave goes to Ed, and Ed splits in half goes to Al, and another half goes to Bob. Okay, every day they do this. started with an equal number of cards each, after the first day A would have half the cards, B would have twice the cards, and so on. Okay, let n be the overall number of cards. And just to simplify the discussion, we assume that this number is such that at every step the number of cards of every player can always be split in half. So we assume that it is divisible enough. Probably it will work with the power of 2, for example. Okay. So the first question is, show that no matter how the cards are initially distributed, after a possibly large number of days, the number of cards owned by each of the 5 friends stabilizes, meaning that it does not change anymore. Okay, the idea is, of course, from one day to the next we will have possibly some changes, but are they going to change every day, or the 5 friends are going to converge to a situation where from one day to the next nothing changes? Of course you have a very drastic change the first day. And of course I'm asking to show this independently of the initial distribution of cards. So you can assume that the cards go, maybe the 5 friends start with A having all the cards, or with the cards equally split between them, as in this case. Okay. Actually, you should ask yourselves another question before this. So, what does this have to do with the course, with advanced business intelligence techniques? Of course, you should find a similarity between this and what we have done with the PageRank algorithm. If you consider the overall set of cards as the total prestige, or suppose that you equate m to 1 and work with fractional numbers, which is maybe easier to do. So instead of considering n as the number of cards, suppose that you consider fractions. So you just remember what fraction of the overall number of cards every person has. So we can deal with, well, let's call them P. Okay, PA up to PE. Let's go by steps. If we call NA the number of cards that A has at a given day, of course we need to add also the day somewhere. Number of cards of A at day T. Then, of course, the sum of the different number of cards, of course, The other problem here is that I decided to call people by name. Well, of course, we are dealing with algorithms, so maybe we should call them by numbers. So let's call the different players I, with I going from 1 to 5 in this case. And of course we know that the sum of all n(I), with I going from 1 to 5, is the total number of cards n. No cards are ever created or thrown away. The number of cards remains the same always. So at every time we have exactly always the same number of cards, but then we can define simply the ratio of cards possessed by, owned by player I, like this. So that we can, here we can talk about distributions. Okay. That the I of t is always between 0 and 1, and the sum of all pi of t is always 1. Okay, so by moving from the number of cards to this ratio, we actually move to the context where we can use our PageRank algorithms to compute the answers to this exercise. Maybe I'll try to switch on also those lights, if I can. Okay, so everything is, can be easily translated to well, this is what we call a Markov process, where we have a distribution at every step and rules that determine how to compute the next distribution. We can also represent these rules by a graph. So we have 5 people, let's call them 1 up to 5, rather than A to B. And we can represent the different transition rules as arrows with a weight that gives how much of the deck of every player goes to another player. So for example, player 1, the first, gives half to the second player and half of his deck to the fourth player. Let's also keep in mind the original name of the people. So for example, B gives half of his deck to C and half of his deck to D. C gives all of his deck to D. D gives all of his deck to E. And finally, E gives half his deck to B and half to A. Okay. Here, of course, we are. So these numbers are actually how each player splits his deck to give it to other people. But you can also interpret them as probabilities. How do we interpret this as a probability? For example, you have n cards. Identify one specific card, for example, the first, an ace of hearts, or if you're playing Pokemon, some specific Pokemon, and so on. So, suppose that you identify one card. This Pi of t is actually, since the cards are swapped, we can assume that cards are swapped at random. We only decide how the deck is split, half and half, but not which cards go on one or the other half. This becomes the probability that at a given time that particular card belongs to person I. Of course, if all people have the same number of cards, they have equal probability of having that card, provided that the original deck was evenly shuffled before distributing, of course. This becomes a graph with transition probabilities, because this is the probability that a specific card in the hand of player 1 goes to player 2 the next day. Okay. Each card in play of player 1 has 1/2 probability of going to player 2 and 1/2 probability of going to player 4. So we are actually dealing with transition rules and probabilities and stochastic processes, stochastic matrices, and so on. Now, okay, I already forgot the first question, which was, okay, no matter how the cards are distributed, show that after a certain number of days, the number is going to be stable. So the number of cards of player A does not change with time anymore, and so on. Of course, the cards will change because decks will still be swapped, but the number does not change. Okay, and of course this is related to the properties of this graph. In particular, question 1 asks about convergence of the process, and asks about unicity of the solution, of the yes, let's say of the stable solution. And we have linked these two properties, these two desirable outcomes of a random process like this. We've linked these two outcomes to two specific properties of the graph, which are the the periodicity and the irreducibility of the graph. So here we must show that the graph is, let's go with some order. Well, if you remember, if we can show that the graph is reducible, then we end up with a unique solution. Reducible graph means that once, for example, some card is trapped within a user, it cannot move to some other user. A graph is irreducible when there is some path from every user to every other user. I still keep saying user, they are players, but here you can easily see that cards can move more or less freely. If a card is with C, it can go to E in 3 steps. Okay, and if you look at it, every pair of people have some way for a card to move to one to the other. The easiest way to show it is, okay, take one of the people and show that a card can go from A to everyone else, and a card can go from everyone else to A. Of course, if you prefer, at this point, we have seen the equivalence with PageRank. You can think of websites and users. It's exactly the same thing. So if you are in A, you can move to B, you can move to C, going through B, you can move to D, and you can move to E, going through D. So the reducibility is quite clear. Irreducible means that if the system can converge, then the asymptotic solution is unique. Convergence well, to prove convergence, we need to show that this graph is also aperiodic. I can't quite remember exactly which definitions of aperiodic I gave to you. Okay. So we just need to, well, okay, aperiodicity means that you have many possibilities of going from one node to another node, and these the different paths that go from one node to the other, for example, from A to D, okay, if you look at the length of all paths that go from A to D, you find almost all possible lengths, with the exception of a finite number. This ensures that things will even out in the long term. For example, from A to D, you can do it in one step. You can do it in 2 steps. Can you do it in 3 steps? 1, 2, 3.
Yes, you can do it from each summing 2 because there is BC. You can go
From A
to B, B to C, C to B, and
but they are actually 4. Okay, so
you can sum to
sorry.
4, 6, 8.
Yes, at this point, yes. So all the even numbers from 4 are possible because of C. Okay. So 6, 8, 10. What about other possible odd numbers? Well, of course it depends. But actually not only even numbers, because you can, for example, do 1, 2, 3, no. Start from A. 1, 2, 3, 4, 5, 6, 7. So 7 steps are possible. And so, yes, but I wanted to show that if you follow this 1, 2, 3, 4, 5, 6, 7, then by repeating this, you have all odd numbers from 7 on. So actually, you can go from A to D in almost all numbers of steps, and also 5, of course, by how did you do?
Like 7 without the B to C. Sorry.
Oh, right, of course. Okay, so the fact that we can go from A to D in almost all numbers of steps, with the possible exception of 3, is a guarantee that the system will even out at least between A and D. But then we have the reducibility that tells us that, well, if you want to go from C to E, you can go from C to A, then go from A to D with an arbitrary number of steps, and then go from D to E. Okay, so in this case you show that between each pair of nodes you can go in an arbitrary number of steps, apart from a small numbers of exceptions, a finite number of exceptions. The definition that I gave to you leads to the same result and tells, okay, if you can find 2 cycles in the graph that are coprime, whose greatest common divisor is 1, then you're done. But of course you have a cycle of 2 here and cycles of 3, and the GCD between 2 and 3 is 1. Okay, so you have many ways of showing that the graph is aperiodic. Please, if you have some doubt.
You can choose arbitrary loops to look for this problem.
Well, once you have shown that the graph is irreducible, it doesn't matter where the loops are, because you can go from one to the other in a finite number of steps. So you mean that maybe the loops should have something in common, maybe one edge or so? No, the fact is that once you have 2 loops with a GCD equal to 1, it means that if you want to find a path from one node to the other with, who knows, 10,000 steps, then you just need to find, well, it's a matter of integer arithmetic. So once you have a GCD of 1, by combination of the 2 numbers you can get every number you wish. apart from a finite number. Then everything else, to go from one loop to the other, you just have a finite number of steps that you can put into your count. So the idea is that if you want to go from node I to node J and you want to take 10,000 steps, then you just need to find a way from node I to the first loop, to one node of the first loop. Then you make an integer number of loops, these loops. Then you need to find a way from the first loop to the second loop. And then a way to go to J. These the steps that you require to go from node I to loop 1, you know it in advance. It's A. Let's call it A. You know in advance the number of steps that you need to go from loop 1 to loop 2. Just need, suppose it's 2, maybe it's B. You know how many steps you take to go from loop 2 to node J. Then you just need to execute loop 1 and loop 2 so that you make this number of steps. 10,000 minus A minus A, B minus C. And this is always possible provided that this number is large enough to accommodate for at least one of the loops. You need to, yes, to have it large enough, then you can do it. Okay. Of course, if loop 1 and loop 2 share a node, then you're just asking for B to be 0. Okay, so the first question was the usual question that you ask when you're looking at this kind of process, for example, at the PageRank algorithm. Is the system nice enough to converge to some good value? Of course, this convergence, well, we know that the system converges to some specific values which we can call pi, without a superscript. Of course, we have been asked to assume that the total number of cards is always divisible by every other number that we can find here. So, the answer is yes, we can show that no matter how cards are distributed, so even if you start with all cards belonging to player A, in a certain number of steps, well, actually, this pi is an asymptotic result. So we end up with pi only after an infinite number of steps. All we can do is that pi of t converges to pi when t goes to infinity. But actually, if you want to observe this, you can also observe that since we are dealing with a finite number of cards and we are supposing that n is always divisible, then this should happen after a finite number of steps. But actually, I'm not asking to be too precise about this. I was just asking to focus on those properties. Let's see the second question. second question is well, now we know that the number of cards becomes stable after a possibly large number of steps. Okay, determine how many cards each player will have. Okay. Now, so basically we want to determine the values, the stable values of Pi. So what should P1, P2, P3, P4, and P5 be in order to remain unchanged after 1 day of swaps? So for example, we know that, well, we just need to look at the graph and build the corresponding equations. For example, the relative number of cards that player A1 will have after a series of swaps is equal to, well, the only player that gives cards to A is E, and he gives 1/2 of these cards. So whatever the number of cards of A, it must be 1/2 the number of cards of player E. The only way by which A receives cards is by E splitting his deck into 2 halves and giving 1/2 to A. So, as we do with the PageRank algorithm, we look for every node, we look at the incoming arrows and we write the corresponding fractions. So, for example, the ratio of cards of player 2 will be 1/2 the number of cards of player 1 plus the number of cards of player 3. C gives all of his cards to B. And finally, 1/2 the number of cards of player 5. Next, player 3 receives all of his cards from player B, and actually receives half of the cards of player B. Player 4 receives 1/2 of his cards from player 1 and 1/2 of his cards from player 2. And finally, player 5 receives all of his cards from player 4. Okay, I think that's it. So in order to find the P1, P2, P3, P4, and P5, we are assuming that they are ratios, probabilities, fractions, so that they are a distribution, so their sum must be 1. We just need to solve them. As usual, there are some inequalities that help us solving this system of equations. So for example, let's write here, okay, of course, this is very important, P4 equal to P5, because we can remove one unknown from the equations. Next, we can look at this. So let's write everything in terms of P5, for example. So P4 is equal to P5 because of this equation. Then, if you look here, P1 is equal to a half P5. So we can, well, let's remove the equations as long as we use them. Here I can replace P1 with half P5, so this becomes 1/4 P5. And by adding this and this, it becomes 3/4 P5. Like this. Here instead of P4 we can write P5. And here P1 is half P5, so 1/4 P5. We can bring this on this side, so here remain 3/4 P5, and so this becomes P2 equal to 3/2 of P5. So we can also remove this equation. Here, instead of P2, we can write, so 1/2 P2 becomes 3/4 of P5. And so we also have P3. And now we have all probabilities in terms of P5. Okay, we use this. We didn't use this equation, but we don't need it. Actually, you can check if. So if you replace P5 here, you should get 0 equal to 0. It can be a check that you make to be sure that everything worked out. So for example, here P3 is 3/4 P5, and here P2 is 3/2 P5, and of course 3/2 P5 equal to 3/2 P5, so it works out. Finally, you need to add up all these probabilities and make them equal to 1. So P1 plus P2 plus P3 plus P4 plus P5 must be equal to 1, and this becomes, okay, P1 is 1/2 P5, P2 is 3/2 P5, P3 is 3/4 P5, P4 is 1 times P5, and P5 is 1 times P5. So you can use this to determine P5. This becomes, okay, we have 4 down here. Here we have 2 plus 6 plus 3 plus 4 plus 4. Meaning Okay, and finally, so P5 is 4 out of 19. So here we can get all probability values. So P1 is 2 over 19, P2 is 6 over 19, P3 is 3 over 19, and P4 and P5 are equal to 4 over 19. So, the question was, okay, expressed as a fraction of the total number of cards, so these fractions are actually the answer, and then it asks to check the solution for n equal to 380. So suppose that the total number of cards is 380. Okay, what happens if the number of cards is 380? So let's compute 1/19 of n, which is 20. Okay, 380, 38 is twice 19, of course. So meaning that the number of cards of player 1 is 2/19 of n, so it's 40. The number of cards of player 2 is 6/19, so 120. The number of cards of player 3 is 3/19, 60. Number of cards of player 4 is 4/19, meaning 80. And also the number of cards of the 5th player. Okay, so if the cards were 380, and of course the initial distribution always allowed for splitting all decks in half, this would be the solution. Finally, that question asked to check the answer on this number of cards. But this is rather easy. So, assuming that A gives half of these cards to B, then next day B would have 20 cards from A, and also D would get 20 cards from A. B would give half of his cards to 3, half of 180, 60, and half of his cards to D, to the 4th player. The 3rd player would give all of his cards to the 2nd player. The 4th player would give all of his cards to the 5th player, and the 5th player would give half of his cards to the 2nd player and half to the 1st player. Okay, so after you add the numbers up, you find that the numbers are exactly the same as before. Okay, so this is actually a stable solution. Of course, we got to this stable solution only by, you see, assuming that n is always divisible. So we moved to a real, a continuous approximation of our problem, which is in terms of discrete. Finally, final question was, okay, third question is, suppose now that Bob changes his own policy and gives his whole deck to Chuck every morning. So instead of splitting his deck half to C and half to D, he gives all of his deck to C. Prove that, in that case, the number of cards owned by each friend does not necessarily stabilize. Okay, so the next question is, let's change this policy. B decides to give everything to C, or player 2 decides to give everything to player 3. Okay, what happens here? So let's modify the graph. This edge disappears and this becomes 1. Now, when this happens, of course, you can see that we actually lose some properties of the graph. Okay, the graph is no longer irreducible. Once a card is given by E or by A to B, it remains shared, either it remains to B or it remains to C. It cannot move. So there are no arrows going out of B and C. So we lost irreducibility. This graph is now reducible. Or let's say it's no more irreducible. Okay. This means that, well, the original graph was irreducible, so we could actually say that the solution would be the final solution where the system converges is unique. Well, no, actually. No, sorry. The graph was irreducible. Irreducibility means that you always converge, right? Okay, what happens here? Of course, the fact that one property falls doesn't mean that what we're searching for is no longer true. We must find an example where we don't have convergence. Can we find here an example where there is no convergence? Can you name one? An easy one?
All cards.
Okay. Please find an agreement. Okay, if you give all cards to B, let's simplify. We only have one card. Okay, we give the card to B. Now the system will be we have P1, P2, P3, P4, and P5. Okay, all cards to B at time t. At time t plus 1, we have that the card has necessarily gone to C. At the next time, the card will have gone back to B, and so on. So in this case, we don't have any convergence. The card will keep moving between B and C. And okay, but can we find stable combinations here? And is there, well, actually the next question was, okay, give the only stable combination. Actually, I could also have asked, is there just one stable combination? Are there many stable combinations? There are no stable combinations. Here you found a solution that is not stable. What if we want to find a stable combination? Okay, first observe that there still are loops with a GCD equal to 1. In this context, well, it doesn't mean very much in this context, actually. Well, name what is the only stable combination here? Can you see it? Remember that this arrow has disappeared, and every time a card is trapped with B, it won't get out of this loop anymore. Any idea?
One half to B, one half to C.
Yes. And that's all. That's it. You see here, B and C tend to act as a sink. Sooner or later, every card will go to B. Remember that every time E or A own some card, there will be 1/2 probability that this card will go to B. So the part of deck possessed by A, D, and E is going to reduce at every step. Of course, we will end up with some indivisible case where A only has one card, so it cannot split it in half. But let's only consider the continuous approximation of the problem. The only, the idea is that all asymptotic solutions necessarily have 0 as the probabilities of 1, 4, and 5 of these 3 nodes. We can see, so it's rather intuitive, okay? Sooner or later, everything will go in the hands of B and C. And the only way we can have these 3 zeros and something here that remains the same one step after the other is that P2 and P3 are 1/2. Because they keep swapping every time, so they must be equal. Of course, you can also show it with equations. the equations for these three nodes are, in this case, P1 is equal to 1/2 P5. P4 is equal to 1/2 P1. And finally, P5 is equal to P4. Of course, you only need to replace probabilities twice. For example, P4 is equal to P5, so here we can write P5. So P1 is twice P5. So we can replace P1 with 2 times P5 here. And the only solution to this is P5 equal to 0. This is 4 P5 equal to, sorry, why 4? 2 minus 1/2. Okay, so 3/2 of P5 equal to 0, meaning P5 equal to 0, and then the value of P5 cascades also to P4 and P1 by the previous equations. So in order to be stable, we need to have those three probabilities equal to 0. So in the case of 380 cards, the only stable solution would be having 0 cards for player A, 190 cards for player B, the same for player C, and none for player D and D. Okay, so this concludes the exercise. That exam actually has 3 exercises. Okay, let me just write the text of the third exercise of that exam, then we can discuss it later. Anyway, I will put this text and also some other text so that next week, which is the last week of the course, we can discuss. Do we have another week? Yeah. Okay. We can discuss exercises. So this is an exercise about MapReduce. Suppose that you are handling a system similar to Google Analytics. Google Analytics receives it's that service that tells you how many visits you have on your website, where they come from in the world, and so on. You only need to add a short snippet of code at the end of your pages, and every time a user accesses your web page, his browser will also communicate with Google and leave a trace of your movements, of the user's movement inside your website. So it's a way of gathering statistics about the usage of the website that you administer. So suppose that Google Analytics logs the time of permanence of each user on each visited web page on a simple text file. I assume that they use something more. So a text file containing 3 fields on each row. A page ID, the ISO country code of the visitor, meaning that Google receives a notification that contains also the IP address of the people that visit your website. And of course, from the IP address, you can often detect the country. And finally, the time of permanence, meaning how long that page has remained displayed in the user's browser before he clicked something or went to some other website. So for example, the site could contain some random number, which is, we assume that every page has its own ID. The country code, for example, this means that the user came from Italy, visited the page while being in Italy, and the page remained in the web browser for 32 seconds. Another random code, UK, 12 seconds. Another random code, IT, 45. Node FR 10. Another code UK 30. And so on. Okay, so suppose that this log is very, very, very large because it records accesses to lots of pages by lots of different people. So that it's stored in a distributed file system, possibly in different files for different websites. So all that we know is that it is the ideal environment where you can use MapReduce. You can see this as a very, very large file that is distributed on many computers. So the question is, what is the question? Okay, provide a basic MapReduce implementation, meaning a mapper, a combiner, and a reducer, that computes the average permanence time per country code. For example, the outcome of this log after the MapReduce would be IT 38.5, UK 21, FR 10. Okay, the average of all times of permanence. Okay. So this is very similar to counting or to adding things, because you have different times and you want to add them together. There are many ways you can do it. There are actually different ways that can take advantage of a combiner or cannot. The idea is that, for example, if suppose that you want to make the simplest implementation of this. The simplest implementation just forgets about the page ID. We don't need it anywhere. And simply we use this as a key and this as a value. The idea is that once the mappers have produced these key value pairs, the reducer, let's write it in here, this is the final result, of course. The reducer will receive tuples in the form IT followed by the sequence of 32, 45. Okay. UK 12, 30, and so on. Of course, a reducer that receives this can simply compute the average of these numbers, so it gives the result. Okay, so this is the simplest implementation. The problem is, can we actually use a combiner in this case? Yes or no, and in both cases, why? So remember, a combiner just makes the same steps as a reducer does, but with within a single server. So it does it partially, only for a subset of information. Can you suggest some? So let's try to do it as the last thing we do today, of course. Suppose that we have two servers, 1 and 2. The first received, I don't know, maybe it had only one record about Italy. The other records are from other countries around the world. The second has lots of records about Italy. And for us, lots means 3. Maybe with 1, 2, and 3. Okay. So the second server has 3 records about Italian visits to some website that is controlled by analytics. This other server only has 1. The idea is that here the mapper produces these 3 records, and the combiner receives the string IT with 1, 2, and 3. And here, of course, it's going to produce this as an outcome. Okay, the average between 1, 2, and 3, of course, is 2. Here, the combiner in this machine receives IT coupled with only 10 as the value part, and so of course it produces IT 10, which is the arithmetic mean of 10. Next, these are sent to the reducer after a combination part and so on. The final reducer receives IT coupled with the 2 numbers 10 and 2. And the average between 10 and 2, so it produces IT 6. 10 plus 2 divided by 2. So the final reducer says that the average time of permanence of people from Italy is 6 seconds. But this is false, because the average between 10, 1, 2 and 3 is 16 divided by 4 is 4 seconds. The problem is that we cannot take arithmetic means in different steps. Or, you see, this arithmetic mean is computed on 3 values. This arithmetic mean is only computed on 1 value. So this arithmetic mean should have more weight when computing the final value. This should be weighted 3 and this should be weighted 1. So, if we want to use a combiner, which in this case is probably very useful because we have, you see, we may have lots of information in every machine, but the actual country codes are less than 300. Okay, there is of course the number of countries in the world is finite, so and it's not going to increase a lot, not in the short term at least. So a combiner would be useful here, because rather than sending all tuples out to the framework, if we use a combiner, every machine will only output at most 300 tuples. But the tuples need to take into consideration not only the average, but also the number of items. The idea can be that the average is computed only at the end. Here, we could write a combiner that outputs. Of course, the key part always remains the country code. But as a value part, it can output actually a pair of numbers, which are the sum of the items and the number of tuples. Again, here, instead of writing 2, which is the average, it would write out IT paired with the sum, 6, and the number of elements, 3. So now the reducer will receive the country code IT together with a list of pairs. So it says this is a sum of 10 obtained by just 1 record, and then we have a sum of 6 obtained by 3 records. And this information now obtained by the reducer is sufficient to compute the final result. So it just the reducer needs to associate to the key 10 times 1 plus 6 of 10 plus 6 divided by 1 plus 3. Okay. The overall sum divided by the overall number of items. We need to remember how many items we have in total. Okay, so the only point to consider here is when considering a combiner, okay, so check it on a real case and see that it doesn't work. At least the simple version of the combiner. Is this clear? Okay, the next question was, of course, the exercise would also ask to actually write the functions. The next question, the final question, it's more of an open question, is, okay, suppose that we have 10,000 machines that can work on this. After the mapper phase, of course, during the mapper phase, all 10,000 machines can be used. We simply split the input into 10,000 parts, and we do it. Finally, we need to run reducers. But there is a strong constraint on reducers. One reducer needs to get all of the values corresponding to one key. Okay. After everything has been output by mappers and combiners, all records corresponding to one specific code, for example IT, must go to the same reducer. Because one reducer needs to aggregate all the results about one key. So we have potentially 10,000 machines that can be used for that, but we only have 248 ISO codes. At least they were 248 when I wrote this exercise last year. Can you propose any mechanism by which we can use all machines for the reducer phase in order to, of course, speed the work up? Okay, this was more of an open question because I would accept any kind of answer, but in that case I would also accept I don't know. But you know, you can propose some modification to the framework or some modification to, who knows, maybe the key part in order to have main keys or whatever. Okay, that was completely open. Maybe we can discuss next time. Anyway, I have also prepared the solution to this proof, so I can post also the solutions so you can have a look at them. Okay, that's all. So, tomorrow the lesson is cancelled. I will post some exercises and maybe next Monday we can discuss about them.